Hello everyone, I'm Fengyu from NVIDIA. Today I'm going to talk about our work collaborated with Dinesh, Shidong, and Srinivas from Carnegie Mellon University on using longitudinal, in other words, long-term self-supervision to reconstruct 4D traffic activity. Here, 4D means acquiring vehicles' shape and pose in 3D world over time. Such information has wide applications such as estimating real-world velocity, locating traffic anomalies, driving assistance, and traffic monitoring for smart cities. However, 4D traffic reconstruction could be very difficult. The first challenge is how to get the data. Depth sensors output 3D information, but are too expensive to deploy at city scale, so we turn our eyes to traffic surveillance cameras as they have been installed widely. The problem is these cameras only collect 2D images. Therefore, we need some accurate single-view reconstruction algorithms to infer 3 or 4D information from them. Current reconstruction methods rely on some 2D detections to locate the vehicle in videos, and then estimate 3D shape and pose from 2D. However, the detector will fail in some frames due to occlusion or unrecognized vehicles. And if we use such off-the-shelf 2D detections to reconstruct 3D, the result will be spatially inaccurate and temporally inconsistent. To solve these issues, we noticed that although detection and reconstruction may be wrong for some frames, traffic activity is repetitious in long term. For example, in a 20-minute video, vehicles passing this complex 5-way intersection can be clustered into groups with similar motion patterns like this, each trajectory representing a typical motion pattern. Using such longitudinal pattern as self-supervision, our method greatly improves 2D and 3D key points in the upper images and achieves high accuracy 4D reconstruction as shown in the lower. In our approach, first we need to get initial 2D and 3D key points before longitudinal self-supervision. We detect 2D bounding boxes and key points in each frame using HRNet. Then, we initially reconstruct the 3D shape and pose of all the vehicles in the long-duration video. Note, most previous methods do this frame by frame or only consider neighborhood frames. By contrast, our optimization exploits several geometric constraints to achieve the long-term spatial and temporal consistency. Here, we need to enforce each vehicle's 3D shape constant over frames, so we apply a multi-object tracker, the visual intersection over union tracker, to get the vehicle IDs. We minimize the sum of two losses. First, according to camera model in the right figure, each vehicle's 3D key points can be projected onto the image. We minimize the distance between the projection and the respective 2D detections. Secondly, we assume all the vehicles in the long-term video to locate on a common plane by minimizing the distance between the vehicle's bottom center and this plane. These initial 2D and 3D key points may not be perfect, but if we accumulate them over a long duration, we are able to extract longitudinal patterns from them. Such patterns can later be used to improve the 2D and 3D key points again. How do we refine 2D key points? In the accumulated 2D detections, there are both accurate and erroneous key points. We distinguish the good ones from the erroneous with a threshold on the reprojection error we got in the initial optimization. We call the good ones 2D experts and use them to refine the bad ones. For example, we find these 4 vehicles have bad key points. Then, for each vehicle, we want to find a 2D expert with similar shape and pose. Since the camera is fixed, vehicles with bounding boxes of similar size and location tend to have similar 3D shapes and pose, so we retrieve 2D experts using bounding boxes in consecutive frames. In the middle are the top 3 neighbors retrieved. Then, we align the bounding box of these experts with the vehicles to refine and update the bad key points with expert key points. we can see the key points get much better. Okay, that's for 2D key points. What about 3D? Because traffic motion is repetitious, all the vehicle trajectories can be clustered into several groups. Previous work does clustering in 2D, but due to camera angles, we notice 2D clusters are not distinguishable. So we perform the clustering in 3D using the reconstruction we got. The mean trajectory of each group is called a 3D expert. If we directly apply a Gaussian mixture model to cluster, the result is shown here. Vehicles in different directions can be distinguished, but like in this blue cluster, the two different lanes cannot be separated. So we need to perform hierarchical clustering on top of these initial clusters. We do this by projection. First, we find the average direction of all the trajectories in one cluster, like this blue cluster. If we project the trajectory points along this direction, the two lanes become easily distinguishable. We do this to all the initial clusters and are able to discover all the fine-grained clusters in the right figure. Here, we show the mean trajectories, in other words, 3D experts after clustering for different intersections. We compare with previous state-of-the-art clustering methods, and ours perform really well and is able to distinguish all the fine-grained clusters. Now, we can use these 3D experts to refine the 3D reconstruction. For each vehicle in continuous frames, the chamfer distance is the distance from its positions to the 3D expert trajectories. In all the 6 experts, the blue expert has the minimal chamfer distance, so it is the expert for this vehicle. We define the longitudinal loss as the difference between the green vehicle pose and the yellow 3D expert pose. We jointly optimize the sum of reprojection, planar, and longitudinal loss to refine the vehicle pose. Here, up and down show the 2D and 3D key points before and after longitudinal self-supervision. The key points become more accurate even if there are field detections in the input frames. Also, the reconstructed trajectories are temporally more consistent. Here, from left to right, we evaluate the key point accuracy on the input frame, reconstructed in 3D, and projected onto another view to verify the spatial consistency. The purple curve is the accuracy using both the 2D and 3D longitudinal self-supervision. On average, 3D and multi-view consistency show 12% and 16% absolute improvement over the nearest baseline. The key of longitudinal self-supervision is to accumulate information over time. So a critical question is how long video should be used. In this figure, we gradually increase the length of videos to extract 2D and 3D experts, and we see the accuracy goes up because the longitudinal self-supervision works. After some time, the accuracy converges, indicating enough 2D and 3D experts has been learned. Longitudinal self-supervision has many applications. Here, we show the 4D traffic reconstruction with vehicle counting and speed estimation. The dashed lines indicate the single-view camera's field of view. We show the reconstructed key points from bird view in each frame and their trajectories in the past frames. The different colors indicate different clusters. We see all kinds of vehicle motion passing this intersection from different directions. The turning cars slow down to wait for other cars and then accelerate. We also use our model to analyze traffic anomalies. If we found the probability of a trajectory belonging to any cluster is much lower than usual, an anomaly is likely to happen. Here, in the first example, left turn from this direction is prohibited. We observe a car breaking the traffic rule. In the right is its trajectory probability. It is lower than the usual normal trajectories. Another case is a near miss. Left-turning cars should yield to oncoming traffic, but this car didn't, so the two vehicles braked suddenly and avoided a collision. The last example is an accident. Here, a vehicle hit a back and stopped in the middle of the intersection. Our approach can record the 3D vehicle location, trajectory, and the velocity when a traffic event happens, which can be useful to find the cause of the anomaly. Okay, thank you so much for listening. To summarize, our approach utilizes long-term traffic information and self-supervision to achieve high accuracy 4D traffic from single-view surveillance cameras. For more information, please visit our project website. Thank you.